everyone. In this tutorial, we will explore 6 powerful root finding methods using MATLAB. From graphical analysis to numerical techniques like bisection, Newton-Raphson, incremental method, second method, regular facet, and graphical method. So let's dive in and see how each method works step by step. So first, I'll explain to you how the application works. So here, this function gets the function as a string from user input, and it converts to a function handle. And here, it validates the function by trying to evaluate it at x equals 1, and if it fails, it stops execution with an error. And so here, it's the interval AB where the root will be searched. So these are the methods of choosing what method you will choose. So here, it displays a numbered list of root finding methods and asks user to select method numbers. You can also select multiple numbers or multiple methods. And here, if you select graphical, Newton-Raphson, and second, this function will show that it is selected. And here, it converts the user input to a symbolic expression, and it computes the symbolic derivative and converts it back to a usable function handle, the f. So this is the f. And here, if a automatic differentiation fails, the user is asked to enter the derivative manually. And for this function, it loops through the selected methods, matches its method name, and calls the appropriate function. Example, bisection roots or Newton-Raphson roots, and uses a try catch to safely handle errors in its method. And here, this is the end of the program. So I will be explaining to you the 6 graphical methods and how they find its graphical methods and how they find its roots. Here, in this function, you set the default parameters. If the user does not provide points, it defaults to 1000, suppose. And if tolerance isn't provided, it uses i.e. -6 as a result to detect close to 0 values. And for this function, if y1 and y2 have opposite signs, a root exists between them. It eliminates the root at the midpoint of the x values. And this, if a y value is very close to 0 within the given tolerance, it's considered a root, and it avoids duplicate roots by checking the distance to the last root found. So here, this shows how many roots were found and where. And here, the plots the function in blue, adds a dash line at y equals 0 for visual reference. So for k equals 1, link root values, plots its root as a red circle, and it labels it with its value. So that's all for the graphical method, and let's move on to incremental roots. Now this is the incremental roots. Step equals 0.001. Call incremental step scan to slide from the start to end in step increments. Evaluate f of x at both ends of each step. If the product function of x1 times function of x2 is greater than 0, a sign change and root exists. Estimate root at the midpoint of the interval. And so here, for each small interval, we evaluate function of xl and function of x next, and if function of xl and function of x next is greater than 0, there is a sign change, so root likely exists between them. It estimates the root at the midpoint and stores it, avoiding duplicates if the root is too close to a previous found one. So here, every scan step, whether a root is found or not, is logged with step number idx, start and end of the interval, and the function values at both ends, or the product of function values to detect sign changes, and the status is root found or no change. This log is later shown in a table for debugging or views. So in here, it plots the function curve f of x in red, and plots the x-axis, the reference line, and marks its detected root with a colored circle, adds a legend and labels for clear visualization. And so that's all for the incremental roots. So let's move on to bisection roots. And here we are in the bisection roots. So here, the method divides the function repeatedly by half. At each step, it calculates the midpoint xm. Based on the sign of function of xl multiplied to function of xm, it selects the half where the root lies, where a sign change occurs. It stops when the interval is narrow enough or reaches maximum iterations. And here, each iteration logs the iteration number, current lower and upper bounds, the midpoint, the function values at xl and xu, and the midpoint. And this data is later shown for a summary table. And in this function, it plots the function curve over the interval, marks the x-axis for reference, and plots its related root with grid markers and displays the numeric values next to it. So that's it for the bisection roots, and let's move on to the Newton-Raphson roots. And now here we are in the Newton-Raphson method. So for this method, the method uses the Newton-Raphson formula. The xn plus 1 equals xn minus f of xn over f prime of xn. So it computes the next approximation s1 and the approximate relative error, and iteration stops when the error is less than tolerance or max iteration is reached. And here, for each iteration, the following are stored: the iteration number, current guess, the x0, the function x0, the function prime x0, the next guess x1, the relative error, and all of these are later used to show a detailed iteration table. So for the plotting of the graph, this is the function of how to plot the graph. This plots the function curve and the x-axis. Roots are marked with colored dots and labeled, and a legend shows which root is which. And that's it for the Newton-Raphson. So let's move on to the regular false method. So here we are in regular false. So this the method computes the new approximation, the C, the false position, and using the endpoints A, B. So the formula of the regular false method is C equals B minus function of B multiplied to B minus A over function of B minus f of A. So then it calculates the approximate relative error using the current and previous estimate, and it shows the root bracket is updated depending on the sign of function of C. The logging of the iteration data. So here, for each iteration, the following are stored: the bracket number, iteration count, current endpoints, the AB, the new estimates, the C, approximate error, function values at A, B, and C, the sign product, f of A multiplied to f of C, used to decide which sub-interval to keep, and all data is collected in a cell array for display. Here, it plots the function curve over the interval, and each found root is marked with a circle and labeled. The x-axis is also shown to help visually locate where the root lies. And that's it for the regular false method. And the last method, the second method, let's move on to. So in the second method, the second formula is calculates a new root approximation, the x2, by drawing a second line through the points x0, function of x0, and x1, and the function of x1, and finding where it crosses the x-axis. The approximate relative error is computed to check convergence. If error is greater than tolerance or maximum iterations reached, the method stops. So for logging of the iteration data, what's being recorded here is the iteration number, the previous two estimates x0, the x1, function values f of x0 and f of x1, and the new estimates, the x2, and the approximate error. These rows are later formatted into a table for full iteration trace using how the method converges to its root. And for the plotting of the salary, blue curve of the function, horizontally gray line y equals 0, circular markers at root locations with colors and tables, legend and labels for better interpretation. That's it for all the 6 methods of how the MATLAB application works. Thank you for watching this tutorial. We have examined and implemented 6 fundamental root finding methods in MATLAB, highlighting their procedures, applications, and differences. This overview provides a foundation for further exploration and comparison of numerical techniques in solving nonlinear equations.